All right. And I'll put 303. Okay, good. All right, so let me switch and find this problem. Oh, actually, why don't I share screen first? So if anybody's looking at the screen, they can see the chapter number here. And this will give me a chance to test to see if I updated my, it was a biosystem update. So far, everything looks good. All right. Okay, so number 37, huh? Where is Physics 123? Ah, here we go. All right, so number 30, let's scroll down here. Oh, we must be about halfway through the semester here. Getting quite a bit. Oh, this is a good one, good practical one. I remember doing this many times in our fiber optics studies and different levels of classes and labs here. But fiber optics have an index of refraction of n and a diameter of d. It is surrounded by light. Okay. Light is thin in the fiber along the axis as shown in the figure. Maybe I'll start there by kind of drawing the figure. And so they've got kind of a cross-sectional view. And hopefully one of the things you got out of this chapter was that the lights can be used in a pipe. We call it a light pipe or a fiber optics, because if it hits greater than the critical angle, and I should say at critical or even greater, it all reflects back in. And so as long as there's not too much of a bend, so in this case, if I have a beam of light coming up and it hits this right here, if this is kind of the bend to it, this would be the theta 1. And if that's above the critical angle, it'll all bounce off. That is, none of it will leak out of the fiber. And so the energy continues to move along the fiber. Now, rays that are, say, in the middle of the fiber would hit here, and rays that are a little more towards the, I'll call it the outer edge of this circle, would hit here. And the big key then is to realize that if you curve this too much, this angle, theta 1, is going to get smaller and smaller, and it could get below the critical angle, and so this ray can get out. And so if they call R the radius of curve of the outer part, with the fiber itself having a diameter of D, if that bend is too much, or put another way, if the radius is too small, the light will get out. Okay. So looking at these rays, and if you have a whole series of them, the one that hits at the smallest angle is this one right here. So this is the one we have to check for. This is one we have to be careful with. Because if this one is at the critical angle or greater, all of these that are further out are also at an angle greater than the critical angle. Because I'll say it again, this one coming in right along this inner edge, coming up and then hitting the outside, that's the one that is going to be the smallest angle. So that's the one we need to test for. And so if this fiber optic is going to work, we don't want any light to get out. I mean, obviously, it could be bent just enough that some light gets out and the rest don't. But if that only happens one time, that's fine. But a lot of these fiber optics bend many times. And if you got the radius wrong, if the technician said, okay, I'm allowed to bend this with a radius of, say, 10 centimeters, and the 10 centimeters lets a little bit of light get out, but there's a lot of turns, 10% of 10% of 10% of 10%, all of a sudden you got very little light left. So it is important that none of it get out. And that means every ray has to be greater than the critical angle. And that's kind of the magical step to this, is to realize which of the many rays would be the one that we've got to focus our attention on. So I'll say it again, it'll be this ray here coming in from this edge. And so that means this distance here would be r minus d. And of course, this distance here is r. And that's where I'm going to say, all right, if I set this up so that this right here is the incidented angle, okay, according to the Snell's law, N1 sine theta 1 needs to equal to N2 sine theta 2. Well, maybe I should keep reading. It is surrounded by air. Light is bent into a fiber along the axis as shown. A. Yeah, find the smaller outer radius r permitted for the bend of this fiber if light is not to escape. So if any light is not to escape. And this is where our critical angle comes in. The critical angle was, something like this. Let's just say we're in the glass. And if we're in the glass heading out, oh no. Oh, so I lost connection already. Last time this was now this was different. This is my bad. This is after I rebooted my phone. Hang on here. Where is my display settings? Yeah, okay. That was the phone going to sleep. I've got it. All right, so let me put it on never go to sleep. Okay. Try this again. Okay, so let's go back to sharing. Yeah, I don't know why that didn't dawn on me. Reboot my phone always turns this screen off, and I usually pretty good to remember that for the morning time, and then I just leave it that way all day. All right. So continuing on with this, let's see. So the Snell's law I was talking about would be if you went from glass into air, light that comes in and hits at some angle theta 1 because it's an index 1 and it hits the air. The critical angle is when the refracted beam goes at 90 degrees, which is a little misleading because it doesn't really go at 90 degrees. It maybe does first initiate to 90 degrees, but with half of it kind of out in the air and the other half in, it drags it back in and ends up in a reflection. So it doesn't really go this way, but it starts that way. So it makes our math kind of nice where we could put in the index of what it's going into, which in this case is air, and we can put in the 90 degrees. And so that is this critical angle. And so sine of 90 is 1, and so we get 1 over the index number 1, which is the index of glass when we move it to the other side. So that gives us some kind of mathematical way of figuring out what that critical angle is. So coming back to my problem here, I was thinking in my head, okay, let's say this is right at the critical angle. Because like I said, the radius as it bends more and more would make this smaller and smaller. So the radius that would give us the critical angle is what I'm going to work for, and any radius that's smaller than that won't work. So at critical angle, and so sine a critical angle, so I'm looking at this triangle right here. And if I look at sine says take the opposite. So this distance opposite is r minus d over the hypotenuse, which is r. So there's the sine of the critical angle. That has to equal to 1 over n. And I'll just drop the subscript glass. Find the smallest radius r permitted for the bend of the fiber if none is to escape. So then I can go ahead and I guess solve this for r. Maybe I'll cross multiply. The right-hand side becomes an r. This becomes an rn minus a dn. Maybe I'll move this. Well, no, what? I'll leave that rn alone and move this r from the right to the left, and then move that negative, which is dn, over to the right. So I can factor out an r and then finish the problem, or finish A, by saying then that I would have r with
your screen.
en.
It froze again.
Oh, bummer, bummer, bummer. And it's not my phone as I was hoping. Let me check something here. Yeah, that looks good. All right, well, back to Zoom here. What's this little icon telling me? Ah. Yeah. I wonder if there's a little. Ah. Okay. Not sure what that little thing flashing, but I have a suspicion that's part of my problem. All right, well, now that I clicked on update, it stopped flashing. That's good. But, all right, well, let me keep going. Hopefully, it won't continue with that. But we'll work around it. All right, so where was I? I was working through the math here, saying this is how we would solve for r. And so dn over n minus 1 would be the mathematical step here that would say, okay, what is the radius? So the radius obviously would depend on the diameter of the fiber optic and also n, the index of refraction. That would determine, how when they go to install it, they know how much they can bend the fiber as they weave it, like they say, through a building. Let's say you have an office and you got a fiber optic coming from the computer. It goes into the wall and they got to move it through the wall. As it kind of wiggles around through the wall, you want to make sure your radius is not smaller than that number. So, and let's see, I don't think they gave us really any number to work with. So I think that's all they want is an equation. Because then B says, what if, does the result in part A predict the reasonable behavior as D approaches 0? Well, I think so. You can kind of see that if we kind of do a little mathematical thing here and say, okay, let D approach 0, that means your radius approaches 0. That means you can bend it more and more and more and more. And that kind of matches the picture. I mean, imagine a kind of a fat fiber bending. Maybe in a comparison to a narrow fiber. And in my picture here, let's see, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, I tried to give about the same radius of turn, but you can see in the fatter fiber, it would come up and hit. And so this would be your angle of incident. And you want to make sure that that's greater than or equal to the critical angle. But for a narrow fiber, this thing's going to hit way earlier, if you will, on the circle, kind of way up there. It's down here, which is going to make the angle of incidence way bigger. So that means you can bend this one to a much smaller radius. And you can kind of see then that the narrower the D gets, the more this is true, and the more it hits over towards this edge. So yeah, I like that result. It does seem to make sense to me that as D approaches zero, the radius can approach zero. And so fibers that are really thin, then the radius is so small you don't even have to really think about it anymore about them bending. Oh, hang on, froze on me again. Wonder if the initial freezing even a glitch, and if I should start over now or struggle through. Well, definitely struggle through for this problem. So let's see. Can get that, especially since we're almost done with this problem. Okay, so what I was trying to draw in my picture wherever it froze here is that, yeah, that makes total sense. As D gets smaller, the radius could get smaller, and that picture kind of agrees there. So let's see, that was B. Does the result of part A predict a reasonable behavior as D approaches zero? As I can't quite read that. Let me blow it up. Let's see. What am I? As that must be N. As N increases. Okay. So let's talk about as N increases. So as N goes big, and I'd feel more comfortable rewriting this so that I don't have two N's battling each other. Let me move this N downstairs so that I get a 1 minus a 1 over N. So as N gets bigger and bigger and bigger and bigger, so this gets bigger and bigger and bigger and bigger. When it gets, I guess, really big, 1 over really big we can ignore. This would approach D. Now, anything smaller than that, we get 1 minus a little bit. So we get something less than 1. So you divide it, you get something bigger than D. Okay, so as our index gets bigger and bigger and bigger, our radius is essentially from something bigger than D to something smaller than D. Does that make sense? That's a good question. So we're saying that as N gets bigger, the radius can get smaller. Oh, yeah. And I like that because, again, the critical angle is determined by this index. And the critical angle is smaller the higher the index. And so as N gets bigger and bigger and bigger, let's see, did I say that right? N gets bigger and bigger and bigger. We go from a something like a 2 radius down to a 1 radius, or D. Don't like the way I said that. I still don't like the way I said that, but I like the fact that it is allowing for a smaller and smaller radius just on the physical ground. Maybe I'll do it that way. I like that on the physical ground because the smaller radius uh, means it's, if in a sense, it's better trapped. And I know with the higher index, it's, better trapped, if you will. The high index is allowing for a smaller critical angle and allows it to get, for lack of a better word, trapped better. So I would say yes. I like that. I like that approach better. So that makes sense. Okay. Back to, I'd be curious how the author might phrase it. Let me jump over here, chapter 31. No, 35. Problem 37. And A. Okay, so A, they got the same number or answer that I did. Good. And then they say as D approaches 0, R approaches 0, seems reasonable. Okay. Then as N increases, R decreases. Oh, they don't really explain it. They just say this is reasonable. Yeah. Okay. So I think that's the best way. Yeah, it does seem reasonable because it's just easier to trap it. In other words, the high index is easier to trap it. The smaller the radius, the harder it is to trap it. So you can actually then, with a higher index, get a smaller radius. That's probably the best way to phrase it. Okay. Oh, they do one more. Maybe I missed something here. Let me come back. Is there another part to be? Yeah, it says, as N approaches 1. Okay, so as N, I'll put it down here, as N approaches 1, now let me just pause with the physics for a moment. As N approaches 1, you're essentially saying this tube is just air. And so you are trying to reflect light that's in air off of air. That's not going to happen. You just can't trap it. You have to have a high to a low. So as we're going to the limit as N equals 1, this is not going to be easily trapped. And so I guess in terms of radius, we would, have to go to infinity, trap it. We would never trap it, actually. But that does match this then. As N approaches 1, we get R approaching in infinity. So as it gets closer and closer, you're having a harder time trapping it because of the index. So that means to make up for that, you have to have a broader angle and eventually infinite angle. Yeah, an infinite angle, I guess, technically is trapped because an infinite radius of bend is a straight line. And so light in air, surrounded by air, is actually trapped only because it never hits anything. There's no bend to it. So it's kind of a silly explanation, but yes, it is reasonable. How does the author put it? The author says when N is decreased towards 1, R minimum, increases. Yeah, and that is reasonable. In fact, when it gets all the way to 1, the only way to trap it is if you have an infinite radius, which means it's a straight line, which I'm not sure I would use the word trapping it. You're never hitting the side, but I guess it would work. Yeah, okay. And that was kind of a interesting play, but I like the first part, A, a lot. Let's see, there's a C. Okay, so the C says evaluate R, assuming that the fiber has, so this is just a plug and chug into a number. So R equals what I have here, dn over n minus 1. All right, so giving you a fiber optic. By the way, maybe this is a good time to point out then the practicality of this. You're going to actually make a fiber optic that is useful and practical. We're really probably talking about, coming back to our picture, something like this, where the diameter of the fiber is really small compared to any of your bends, and then you have no problems. And that's the idea. So the real key to fiber optics is to make sure the fiber is pretty small. And in this case, they're saying the fiber has a diameter of only 100 micrometers. Now the index of refraction they put at 1.4. So 1.4 minus 1. And so this would be a curious number. They seem like very reasonable numbers to the real life. So 100 microns times 1.4 and then divided by about a 0.4 give me about 3.5 times 10 to the minus 4. Maybe just to put it in something useful, I'll go 0.35 times 10 to the minus 3 because that is millimeters. And so you could bend a fiber like this really tight. I mean, its radius is, 0.35 of a millimeter, which in terms of diameter, that's still, even the diameter of the bend, if I, had something flexible here, here's my power cord to my laptop, but, you can bend this really tight. You're talking about a diameter under a millimeter. I mean, I can make a circle, Anyways, it would be very hard for you to bend the fiber that much. And therefore, you don't really need to think about it. You're like, hey, just here's a fiber optic, lay it out, lay it through the wall, build the building, and we're going to have a whole network going. Oh, nice. So hopefully that will help helpful. Let you guys have a question. I'll see if anybody threw anything up into the chat after all of this.
Yeah, that was good. Thank you.
Good. All right. Okay, well, in fact, that's just the two of you. Got some 121 people today, but I didn't. I wondered if I'd see many of you guys from 123. Given you just took that.
I couldn't come in the morning because we had a engineering test.
Okay. Well, yeah, I guess, and all the more reason you just took a physics test, and usually when you take a physics test, you're so busy focusing on that and not other things that you got other things to make up on. And
yeah,
I don't want to belittle this chapter because some of the algebra can get pretty tough, or maybe I should say the geometry and trigonometry in it. But for the most part, it's pretty straightforward. It's the first chapter, and we always start kind of easy and get hard. And
yeah, actually, 29 was giving me problems too.
Okay, so let's we'll try number 29. But what I was saying here is, wouldn't surprise me if too many people haven't worked on it yet, and or haven't found too much difficulty yet. Although I have found in the past that when students, once they get started on just some of the geometry or the trigonometry, they find they're a little rusty on. They're like, oh, okay.
And yep, so definitely on 29, that's how I felt.
Yeah, it can be a little bit of a wake-up call. Okay, so let me write this down. Chapter 35, number 29. Looks like we are at 332. And I'll scroll up a little bit. What is 29? 29. A triangular prism has an apex angle of 60 degrees. All right, so let me kind of draw my little triangle. One angle is 60 degrees. If they don't say otherwise, I might just make the whole thing an equilateral triangle. Usually that's kind of irrelevant because the light comes in one side and the other, and only the apex angle matters. So I have a feeling they're going to be just talking about the apex angle. So you know what? I probably even shouldn't label these because maybe they do that. Who knows? All right, but apex angle. So Triangular glass prism with an apex angle of 60 degrees has an index of refraction. Okay, so n equals 1.5, and that's a common number for glass, so it's probably a glass prism. Oh, it even says triangular glass prism. Show that if the angle of incidence at the first surface is 48.6 degrees, light will pass symmetrically through the prism, as shown in figure 17. I don't think I need to look at 17. I think I'll use, if they have what they mean by symmetric is that it would go parallel to the base of the prism. And so the light would come in. I draw a normal. It would then bend and go parallel to the base. And the reason they call that symmetric then is because then exiting, it's essentially the same as entering, just in reverse. And so if you draw a normal here, then the symmetric of it is that it, this angle here is this 48.6 degrees. And so over here, we're at 48.6 degrees. And then maybe I should. Let me just go look at, let's see, chapter 35. I've got the book started. Okay. And figure 17. There's 16. Oh, there's 17. Yeah. So this is exactly what they're showing. And by the way, as a side note, this figure 17 is in example number 5. And it gives a nice little mathematical way of finding the index when you're at this angle. And I point it out because that little formula and that mathematics is an important part of next week's. No. One of the labs. Next week must be the week following. All right, well that's far down the road. So, anyways, you'll see that I use that formula there in the lab, and keep pointing back to it in the book. Okay. Anyways, I did get the right picture. Let me come back to the question. So, all right, it says show that this angle of incidence, the light will pass symmetrically through. All right. So what I'm going to do is use Snell's law, the law of refraction, and I'll just write it first. N1 sine theta 1 equals N2 sine theta 2. And I'll apply this as it is entering the prism. So as it enters the prism, it's in the air, so the index is 1. And they're telling me the angle coming in is 48.6 degrees. And it's going then, of course, into the glass prism, which they told me was 1.5. So that will give me the ability to calculate the refracted angle, angle number 2, which my diagram's kind of busy there. So maybe I'll point at it instead of try to draw it in there, and I'll use a different color. So that right there is theta 2, little angle between the normal and the ray. All right, so grabbing my calculator and checking if I am in degrees or radians. I am in degrees, okay. And then putting this in, I get 1 times the sine of 48.6. And then if I divide that by 1.5, I get the sine of the angle. Then if I do an inverse trig function of that angle, oh, it's 1/2, so it's going to be 30 degrees. This comes out to be 30 degrees. Okay, so 30 degrees. Now maybe I'll draw that a little bigger. So what we're saying here is this is the perpendicular. And this is the ray in the prism, because this up here is the apex angle, 60 degrees. And they're saying that I just, calculated this out to be 30 degrees. That would mean, of course, because this is the normal and this is the glass, this whole angle here is 90 degrees. So this is another 60 degrees. Anyways, in the picture, they showed an equilateral triangle. So this is 60. What that would be saying then, that this line here, the ray, is in the same direction as the base, right? I guess if you have two lines, and these would be called corresponding angles. But if the corresponding angles are equal, so you got two lines cut by a transverse, and if the corresponding angles are equal, then those two are parallel to each other. And so I guess that's enough for our proof to show that it does pass through parallel, which is the phrase they use, although they use the word symmetric to, so. All right, so that would be A. If I go to B, B says, it says, find the angle of deviation, D minimum, and it's a Greek letter delta, I guess, for theta equaling 48.6 degrees. Now again, in that example problem, and again also in the lab, if we have a beam coming up and we put a prism in front of it, okay, the beam would have gone in this direction. But in our case, then it hits and goes parallel and then comes out and goes down again. So the beam actually changes its path twice, once going in and once going out. From where it would have gone to where it is going, this right there is referred to as the deviation. So it's really asking, what did this glass block do? How much did it change its direction? How much did it deviate from its original path? Okay, so we come back to the part A that we just did. I guess I would say, something like this. At the first interface, it was going straight and then bent down that much. So in other words, the difference between this input angle, theta 1, and this, I'll call it the output angle, refracted angle, theta 2, is how much it deviated. So in this picture, this angle right here would be how much it deviated. And then again, where it would have gone on the way out would be here, and where it did go is down here. So that's the deviation there. So there's two deviations. And so the total bending, the total change of direction is the sum of those two. Now, in this case, it's fairly simple because they gave us a symmetric one. And so the difference between theta 1 and theta 2 coming in is the same as the difference between theta 1 and theta 2 coming out. So if I take, theta 1 minus theta 2, which they said that was the given, it's coming in at 48.6. And as we just calculated, we calculated that after being bent by the prism's first surface that is going in, we would get a total then of 18.6. I shouldn't use the word total there. I should say we got a bending of 18.6 right here at the first interface. And so if we double that, because it's going to do it again coming out, 12, carry 1, 16, 17, 2, 3. Okay. Guess I need to practice doing math in my head here. All right, but it's 37.2 degrees then would be this deviation angle. 37.2. It has been, this light beam has been redirected by that much. Now, I'll also say that, and this was the whole point of example number 5, and the reason why I'll keep talking about it when we get closer to the lab, is if you then take this prism and you set it at any other angle. So if you can imagine this prism and maybe rotating it at any angle counterclockwise or any angle clockwise, doesn't matter which way you go, the deviation of this beam will actually be more than 37.2. You get your smallest amount of deviation when you get this symmetry effect. That is, when the ray going through the prism is parallel to the base. That's when you get your minimum. And that's what the author is trying to talk about and show in that example 5. But it's also why in this problem, the author says, find that deviation angle. And he calls it then delta minimum. And said, look, this is the minimum because this is the scenario where we are symmetric. In other words, any other calculation, and it looks like that's what he's going to ask us to do next. He says, okay, find the angle of deviation if the first face coming in was at 45.6 degrees. And so that's something a little different. And so I claim, without even doing C yet, is that, hey, this deviation is going to be greater than that. This is the minimum deviation. So 37.2. In fact, jump over to the solutions before I continue on. Make sure we got the same number here. Let's see, for A, he's got exits, so it's symmetric. I probably should do a little more proof that it's symmetric. He does one step. I like it. But B, we did get this same number. Let me come back to A. Instead of just doing a hand wave and say, well, look, if this is 30 degrees and it's parallel, then it's going to do exactly the same thing. He kind of shows that. So perhaps I should too. And let me make a four-sided object in this kind of sea green here, or light blue maybe. It's not really a sea green. But this is a four-sided object. Usually it's referred to the shape like this. It's called a kite. But the total angles of a four-sided object, a quadrilateral, is 360 degrees. Okay. So keeping that in mind, actually, maybe I won't even do that. I'll just do, if this goes, this is 30 and then this becomes 60. 60, 60, that makes this 60. That's probably better, a triangle, 60, 60, 60, which makes that 30. And that's what I wanted to prove, that that inner angle right there is 30. And then, of course, now you have Snell's law with a 30, and the other angle then would be 48.6. That's the same mathematics we did going in. We would be doing the same mathematics going out. So if we, the two that go together is the 48.6 with the 30. So over here, if we have the 30 coming in to this second interface as it exits the prism, then we're going to calculate a 48. So I won't actually calculate the 48. I'll kind of fall short of that and just say, look, it will calculate out to be a 48. But it was kind of nice to show the 30 and the 48 coming out is going to match, and that's the symmetry as the 48.6 and the 30 coming in. Yeah. So he did a little better job of completing number A, or part A. And then part B, we got the minimum deviation angle. So now, I think a little bit harder is going on here to C. Oh no, froze. Okay. If it lasted a little while. I know in the first one, I told myself I might reboot things or put up with it. But I'll just keep working through this one. Okay, so I was, when it froze, I guess I had this page back on top there and was trying to show you that the author did a little better job of proving that it was symmetric. So I'm glad I came back to this. But then in part B right here, the author and I got the same thing here, 37.2. But then the author says, okay, let's try a different angle coming in. Let me go back to the questions. He says, find the angle of deviation if the angle of incident on the first surface is a little smaller. What is it, 45? So I'm just going to put here and put a little smaller angle as it comes in. So this is 45.6 degrees. And what that will mean then is this angle, as we will soon show, coming into the glass prism. So here's my apex angle. This is going to make a little smaller angle. And last time I called this one, I pointed to it with a little green line. I called it theta 2. So let's see what theta 2 comes out to be this time. And maybe just to re-show you the calculation back on A, we just applied Snell's law to figure out what theta 2 was. So let's do that here. So N1 sine theta 1 is equal to N2 sine theta 2. And so again, we're starting in the air. We're coming in at a little smaller angle than in A, and we're at 45.6 degrees. We're still going into the glass, so number 2 is 1.5, and then we can solve for theta 2. All right, so if I grab a calculator here and turn it on, this would be 1 times the sine of 45.6. Divide that by 1.5, and then take the arc sine, and we're looking at, yep, just a little bit smaller, 28.44 degrees. That's our little smaller angle there. Okay, so right there. Maybe I over-exaggerated in my picture, but I want you to kind of see that. And then, of course, going to make the second interface a little bit harder because as it comes down here and hits, and I draw a normal, this is the angle I want. Huh. And that angle, I'll do a little, I guess, geometry. Now remember that this back here, the whole angle is a right angle. And we just said that this theta 2 is at 28.44. So that means if I subtract it from 90, I can get this angle here. So 90 minus that last answer gives me 61.55. Now I say that because I do have then a triangle here up at top. And the sum of all three of these add to 180. So that means I can get this angle right in here. Now, it's not quite the angle I want, but it is the complement of it. So that's going to get me to it. So why don't I take the 180 degrees for a full triangle and subtract not only the 60 at the apex, but also my last answer. That's going to tell me this angle is 58.44, which then I can get what I really want for the exiting beam of light, which is this angle, because that would then be the 90 degrees minus that. And so now we're looking at 31.55 degrees. I hope by writing over my equations, I didn't make it too messy. But applying, I think I can just kind of fit it here. Snell's law again. I'll say N2, or sorry, N1, sine theta 1 is equal to N2 sine theta 2. So applying this to the exiting beam, let's see, we're in the glass coming out. So the N1 would be the glass, 1.5. And the incident angle is why I went through all this geometry to get 31.55 degrees. It's going to exit into the air. So the index of the air would be 1. And then I can find the theta 2. And as I said, even though I didn't actually do the math back on part A, that would have been how I would have showed it was the 48.6 degrees, because I would have put an input angle of 30 degrees. But this one, we've got an input angle of 31.55. Okay, so let me find theta number 2. So 1.5 times the sine, 31.55, enter. And then the inverse or arc sine of that number means we are 51.7, and I'll go 7.1 even degrees. So if I try to get that into my crazy picture, means it would bend away from the normal coming out. And that means this would be 51.71 degrees. Okay, so now I have what I need, although I still got to finish the part C here. Oh, and it looks like part D we're going to do a lot the same, so that'd be good to see it another time. But coming back here to get my deviation angle, I would ask myself, back here in this picture, how much did the direction of the light change in both cases? So coming in and coming out. So the difference between these two angles, which looks like it came in at 45.6 And after refraction, it was 28. So that's what we got from the first interface as it was coming into the glass. It came in at this angle, but it bent, and now at that angle. And so the difference between those is how much it has deviated. And it's going to do that again here. It's going to deviate. It's coming in at 31 and change, and it's exiting at 51 and change. And so the difference between those. So plus, I'll put the big one first, 51.71 minus 31.55. And so let's see what we get here. 45.6 minus 28.44. Okay, so the angle changes by roughly 17 degrees coming in. Well, and sadly, yet again, the phone froze. Didn't see that 17 calculation, did you? Let's see if I can make another calculation, but I will. It's making the connection. Calculate the second part of this, or maybe I won't. It made the connection already. Okay, so this first part here, and I'll just write it down, is 17.16. So that's the deviation again on this first interface of the light. Of course, then it deviates again coming out. And so that's the 51.71 minus the 31.55. And so that's the 20.16. Looks like 2/16 make a 32 and then a 37. So this is not much bigger. Remember, the minimum deviation I got was 37.2. This is 37.32. But then again, you can see that they didn't change the angle by much. It would be like back in A, where they had it coming in at 48.6. It looks like if we took this prism and rotated it counterclockwise a little bit, we would make that angle coming in smaller. And that's what we just did mathematically here. We made the input angle smaller, which of course made the deviation of the first one smaller, but it made the second deviation one bigger. And the sum of the two is what we see coming out. And so what we see coming out of this is a deviation of something greater. And I claim that it doesn't matter which way you move the prism. In fact, that's probably what D is all about. Let me look at D, but I bet if they give you a number so that you move the prism the other direction, you would still see that the deviation is great. Let me see here, part D. Find the angle of deviation if theta 1, yeah, there it is, if theta 1 is 51.6. Okay, so I'll say it again. What we did in A was an angle of 48.6, and that gave us a deviation of 37.2. And they're trying to point out that that is the minimum, because if you take that prism and rotate it counterclockwise, the angle gets smaller, and they said 45.6 degrees. Now what they're going to do is to say, imagine taking this prism and rotating it clockwise, so this angle gets bigger. And that's what we're going to do now. And two ways to do this. I'll do the short way first, but then I'll go the longer way. It's good to see it again. But they said if you've rotated it a little bit, this input angle is actually now a little bit bigger than part A, which was like 48.6. Now we're at 51.6. And they want to show you that where the beam would have gone compared to now where it is going to go, something like this. The deviation angle is greater than that minimum one in part A, which was, or we calculated in B, 37.2. Now I could do this a short way and cheat, but let me not. But I noticed that the number they gave us was pretty darn close to the number we got at the end. We got 51.7. And other than maybe a little bit of rounding, we would have gotten 51.6. So I have a suspicion that our numbers are going to be everything just with the ray going in reverse. And so the same deviation here and the same deviation here. And when we add them together, we're going to get the same deviation of 37.32. Again, proving the point that if you're at the minimum deviation, rotating it counterclockwise or rotating it clockwise makes the deflected beam deviate even more, and hence the name minimum deviation angle. So instead of me just saying the angle of deviation is going to be 37.32, let's work it out. Okay, so following the same thing for the third time, maybe going a little bit faster, but also now you can kind of drive the message home. Let's see if I can find this angle here, which called theta 2, by using Snell's law, n1 sine theta 1 equal to n2 sine theta 2. Coming in, it's in the air, so that's a 1. The input angle, they say, is 51.6. We're going into the glass prism, 1.5, and I'm trying to find that theta 2. And so grabbing my calculator, here I will put sine 51.6, enter. I will divide that by 1.5. I will then take the inverse sine, or arc sine might be a better way to describe it, of the answer, and I get about 31.5 degrees, 31.5 degrees. Okay. Which, by the way, in my shortcut method, yeah, there it is right there. There's the 31.5 degrees going in reverse. Okay, but doing the long way, now that I know that this one here is 31.5, I can then subtract 90 degrees or get its complement. And that means this angle here is 58.5. Now remember, the apex angle is 60. So then I can get that angle because I can go 180, subtract the apex angle of 60, subtract the other angle of 58.5, and I get this angle at 61.5. Which means then I can get the angle number 1 for the light that's exiting, because 90 minus that 61.5 is the 28.5. So the angle coming to the second interface, the input angle, or angle 1 for second interface, is 28.5, which, by the way, in my shortcut method, yep, going in reverse, this one has 28.44. So other than a little bit of rounding, it's just following the light in reverse. Okay, so now applying Snell's law again, n1 sine theta 1 equals n2 sine theta 2. This one is starting in the glass, so 1.5. And then the sine of, looks like the 28.5 is what we came up with for the angle of number 1 over here on the second face. And then it goes into the air, so N1 is, or N2 is 1. And then we can find then angle number 2. Okay, so having a calculator here, I can go 1.5 times the sine of 28.5. Hit enter. I guess divide by 1. I don't need to do anything for that. Then the inverse sine of that answer gives me an angle of about a 45.7. And again, that is the final angle here if the light was going in reverse from my shortcut method. All right, so I really knew all those angles without doing the math. It was just really the same math. So it doesn't surprise me they come out to be the same angles. Just the, like I said, it's just the light.
Again.
Froze again.
I don't think your software update worked very well.
No, I do not. I totally agree that something didn't quite sink in. I'm kind of having a little memory of I looked at my software update and it said the last time, and it gave a late January. And I remember doing it late January and having the same problem with it freezing. And then I did the update thinking that would fix it, and then it didn't. And then the next time it did. So, so maybe I didn't completely get it updated, or I don't know. Anyways, I guess I'm kind of hoping that's what's going on here. So I'm going to play with it this week. But I did the update and then I did reboot, but I'm still having a lot of freezing problems.
Yeah, I have no idea what could be causing that.
But it just loses contact and all right. But I'll just struggle through for the rest of the day. We got just 20 minutes here. So right here, this one, I think when it froze, I hadn't quite written the answer to 45.7. And then after that, I jumped over here and I said, yeah, it doesn't surprise me because back here on my cheating method, if you will, where I would say, look, this should just all be the same numbers in reverse. I had a 45.6. And so sure enough, 45.7 doesn't surprise me. And so again, when I go to ask what is the deviation angle, I would look at this and say, all right, it deviates in the difference between these two. Okay, so because it was heading at an angle of 51.6 degrees, and now all of a sudden it's at a 31.5 degrees. So that's part of the deviation. And then the other deviation is the difference between these two, which I didn't put the 45.7 in my diagram. Let me do that now. But this would be the 45.7 and then minus the 28.5. And let's see what I get. And I'm pretty sure we will get that 37.3-ish. And so that one plus that one added together, yep, 37.3. So I think it would have served the author well if he would also pause for a moment because I think this is what the author's trying to get student to see here is that, I'll say it again, way back in A, when we had it going across in a symmetric way, we got a deviation angle. And we got a deviation angle of 37.2. If you were to move this prism, and move maybe is the right word, rotate the prism. And so in C, we rotated it counterclockwise. And in D, we rotated it clockwise. And we only did a small rotation, but either direction would result in a bigger deviation. And so there is such thing, what they call the minimum deviation, and it's when the light goes through the prism in a symmetric way. And it can be very practical and very useful. And like I said, you're going to do a lab with that because you can actually see very well where the light's going. And you can then adjust the prism. You can rotate the prism clockwise or counterclockwise until this is at a minimum. And then once it's at a minimum, knowing these angles, you can get the n. Now, this problem, they gave us the n and we had to find the angles. But in the lab, we're going to get the angles and then use that to find the n. So that's kind of what we're after in the lab. And we're also in that lab trying to show that the n is slightly different for all the different colors. We call that dispersion. I know we didn't do any dispersion ones here today yet, but probably next week you guys will be asking about the dispersion ones. But the index you got to be a little careful with because it varies a little bit from one color to another color. And so in the lab, we're going to be asked to figure out what the n is for those different colors. Sadly, it crashed one more time here, or another time, I guess I should say. There's going to be a lot. Anyways, so I'll reconnect the phone there and say, I think we answered it. Maybe I'll check the solutions here just to make sure I got the same as the author. What number was this one again? I lost track. Number 29. Oh yeah, I was already looking at the answer, and they got 37.3 both times to kind of show what was going on. Nice. All right. Well, I didn't see you throw another one up there in the chat room.
I have a question.
But go ahead.
We do 31, the next one.
31, sure.
Isn't that the one that I asked about first?
No, you asked about 37.
37. All right. Yeah, I'll start 37. Give me 1 second here. I need to check on something. All right, thanks for being a little patient there with me. Okay, so I think I heard 31 here. So chapter 35, number 31. Nice. Okay, so let me put that on here. Chapter 35, number 31, and the time is 4:18. And I'm feeling lucky like our phone won't freeze. Probably wishful thinking. Wishful thinking. But don't say that. No, knock on wood. Okay, so 31 here. 31. Oh, okay. So 31 is kind of what, yeah, I see why you're following this with my comment. They're showing the light coming into a prism and then spreading out. Let me draw this picture. And so white light is made up of all the different colors, and there'll be some bending going on. But since the index is slightly different and the index is bigger for the violets and the blues than the reds, there'll be a different amount of bending, and the violets will bend the most and the reds the least. And I'll put just green here. I won't try to fit the whole Roy G. Biv in here. But from the extremes here, there would be then this light that's coming out, and the direction of travel will be different for the different colors. And we froze already. Knew we wouldn't get too far, but that's okay. We're going to fight through this last one here, I think. Okay. There we go. Got to click on the computer first. Okay. Now it's spinning around. Okay, so let me read the problem on this. Is still trying to connect here. But it says the index of refraction of violet light through silica flint is about 1.66, and that for red is 1.62. Okay, so there's what I was saying, that the index is slightly different. So if we just want to talk about light in general, we can just say the index is 1.6. But if we want to be very particular about a color, we got to be a little more narrow, and that's slightly different. So that's our dispersion effect. So the different colors will bend a different amount, and so that's why a prism will take the light and spread it out into its rainbow colors. It says, what is the angular spread of the visible light through the prism for a prism that has an apex angle of 60 degrees. So this is a lot like the last problem. If the angle of incidence is 50 degrees. Here we go. 50 degrees. All right, so let's do this. This is really kind of a repeat of the last problem, but I'm going to do it once for red and once for violet. So both the red and the violet would have gone straight out in this direction. Okay. But there will be a bending at the first surface coming in, and there'll be a bending at the second surface. So let me call this red. Maybe I'll even split my paper. I wonder if it'll get too crowded if I try to squeeze both red and violet here in together. But for red, I would say coming in here, I would go N1 sine theta 1 equals N2 sine theta 2. And putting in our numbers, so we're starting in air, we have an input angle of 50 degrees. For red, the index is 1.62. And then that will allow us to find angle number 2. And so that will be the first bit of the deflection of red light. So 1 times the sine of 50 degrees divided by 1.62 inverse sine. And we're looking at about 28.22 degrees. Now, again, like the last problem, let's follow this through. Maybe I'll even grab my picture from the last problem, because this would be the 50, and the angle that I'm trying to say is theta 2 is that one. But in order to figure out what I need next, which is this angle, the angle number 1 on the second interface, I've got to get that angle, which means I need to get that angle. So let me do the 90 minus this last answer. And that would be then this angle right there. And so maybe maybe I'll draw it right here. That the light actually angling down a little bit, because that would be the 61.77. And so I can get this angle by taking a whole angle in a triangle, 180 degrees, subtract the apex angle of 60, and also subtract that last answer, and I would get the 58.22. So finally, then, if I take 90 and subtract that angle, aha, I get what would be this angle in the picture, this angle coming in. And so theta 1, so I'll go N1 sine theta 1. And that sine theta 1 on the second interface is the 31.78 degrees. Okay. And it is in, so here's the light coming through the prism. It is in the prism, so the N1 is the 1.5, and it's coming out into the air, so that's 1. And then we can get the sine 2. So we can get angle number 2 on the second interface. And so that would be, in this picture, that angle. It's not going to come out to be that number because our numbers are different between the last problem and this problem, but that's the picture of this angle. Okay, so let's see if we can find that. What I'll do is I'll just go sine of the last answer, multiply it by 1.5. Let me take the inverse sine, and this comes out to be 52.18 degrees. Okay, so to get the total deviation of the red, I got to remember it came in at 50 and then left the first interface at 28.22. So 50 minus 28.22. I need to add that to, and then here, the difference of 52.18 minus coming in at 31.78. So the entire deviation angle would be 50 minus 28.22. 21. This other one would be 52.18 minus 31.78. And if I add that one with the previous one, 42.18. All right, so 42.18 degrees is the total deviation of a red beam. Okay, so again, hopefully you kind of see the same thing we were just doing on number 29. So let's go through the same kind of thinking for violet light. So if I start with N1 sine theta 1, N2 sine theta 2, and the same idea that the violet light also starts in air, also hits the first interface at an angle of 50 degrees, goes into the prism, and here's where it
Could you
gets
slide the book over a little bit?
Oh, yeah, sorry.
Thanks.
Yep. So the so back here a little bit. So So the violet starts in the air and hits it at 50 degrees. Then it goes into the glass prism, and here's where the difference comes in. The violet has a slightly higher index, meaning that it travels a little bit slower in the prism. And it does that because of the interaction's a little different. Different frequency, a little different interaction. Okay. But that slightly different interaction results in a slightly different angle, and that's why the violet is going to be at a different direction than the red. So if I grab my calculator here and go sine of 50 degrees, and I divide it by 1.66, and I take the arc sine, I guess I would have 27.48 degrees. And so you can kind of compare that to the red here and see that, oh yeah, the violet did bend a little bit closer to the normal. See, it's closer to the normal. Not by much, but a little bit. That time it disconnected me again. Let's see if I can freeze. It just disconnected. See what this does. Okay. All right. So I'll wait a minute for this to pop back up, but I will say it's kind of the same lines of thinking. That okay, now that I got angle number 2, I could work on angle number 1 for the other interface, and maybe I'll do it with this picture again in mind from the last problem. So I really have this angle number 2. Now I know in this diagram it says 31.5, and for us it really is the 27.48. Okay, but see, that allowed me to get this number here. So I'll do my calculator work so you can see it. So if I go 90 minus that would say that this angle here is the 62.5. So to get this angle right there, I would go 180 and I would subtract the 60 at the apex angle. And then I would subtract the last answer, which is this one right here, which is in my case 62.5. And that's going to give me this angle right here, which would be 57.48. So to get the one I really want, which is right here, I'm going to go 90 minus that last angle and get 32.52. So 32.52 is really angle number 1 at the second interface. Okay, so if I do my n1 sine theta 1 equals n2 sine theta 2, so there's Snell's law. And as it's coming out, that means at the second surface, it's in the glass. Oh, just noticed a mistake I made on the red. So we'll come back to that. Let's stay focused on this. All right, so it's in the prism, which is 1.66, and it's sine of the 32.52. Of course, then it's going into the air, so that's 1. And then it would be sine of theta 2. And so this will allow me to find my theta 2. And so let's see, 1.66 times the sine 32.52. Then the arc sine of that would be 63.18 degrees. All right, so I can't seem to get my mind off my mistake on the red. I'm going to fix that. But
Was it the N value?
yeah, I back here,
Yeah, I noticed that as soon as he said it, and I was like, oh.
okay. Yeah, I must have mixed it with the last problem because the last problem had an index of 1.5.
Yeah.
And it looks like up here I did it right. I did the 1.62. So I'm going to come back and fix that, but let's complete the rest of the violet to get the total deviation angle. So at the first interface, we were coming in at 50, but came out at 27.48. Okay, so that's the deviation of the violet at the first interface. Let me add that to the deviation of the violet at the second interface. So it comes out at 63.18. It went in at 32.52. Okay, so the deviation would be 50 minus 27.48, that number, together with this number, 63.18 minus 32.52. And if I add those two deviations together, we're talking about a total deviation of 53.18. Okay, so that's for the violets. Now let's fix my problem with the red. The red theta 2 would be wrong because coming out for some reason, and I think I know why, I put 1.5 for the index, and that was actually the index for the last problem. So this should have been 1.62 like it was above it. Let me cross that out and get a better angle for number 2. So 1.62 times a sine, 31.78. And then the inverse sine of that is 58.56. So then down here, when I go to calculate the total deviation angle, I think this is still right. 50 minus 28, that's from the first one. But then this right here would be the 58.56 minus the 37.58. So let's try that again. So 50 minus 28.22. And the other one is the 50.56 minus 31.78. And if we add those two together, we get a 48.58. Okay, now we're not quite done, but pretty close, because it then asks, what is the spread, the angular spread for the light after it passes through? So in other words, how much do these differ by? What direction is the red headed compared to the violet headed? And they're each heading at a slightly different angle. And that's the angular spread that they're talking about here. What is that spread? So 53.18 minus the 48.56 gives me an angular spread. So the rainbow, if you will, would be coming out and occupying not quite 5 degrees, but somewhat close. Which, by the way, as a side note, all of these numbers are just about dead on for, except for the input angle. Yeah, the input angle's off a little bit. But the index of refraction, the apex angle, the angular spread of the color of light, this is exactly what we're going to do in our second optics lab. So not next week, which is our first one, but the week after, which is our second one, we'll hook up a little prism and kind of look at the rainbow coming out. In fact, let's check the solution here. They got 31. An angular spread out of 4.62. Good. Although, why do they have something different here? Oh, I see what they did. Okay, and that's fine too, because they're ultimately just after a difference. So that you could have just subtracted those two, huh? The 58 and the 63. That would have been a little easier. Whoops, looks like I lost it again. I see. So they didn't do the whole deviation angle. They just did the angle of the last time coming out. That was smarter. But I guess my mind was focused on the whole deviation angle. Wouldn't change it. All right. Well, I guess I'll try to connect here one more time. And crazy thing, I don't see another question in here. So once you guys are dying to see another one, I want to reboot my system. See what's going on.
Yeah, I'm all good.
Yeah, me too. Thank you.
Thank you.
All right. Well, like
Good.
always, feel free to shoot a question by email, and I'll make videos, and I'll keep working on rebooting my system, and maybe my Wi-Fi needs to be rebooted too. Who knows?
Well, it's past 4:30, so your time's up anyways.
Yeah. Okay. All right, guys. Take care and study hard, and I'll get back to grading your guys' test this evening and tomorrow. And I think I should have enough time on Sunday to complete them. I know Sundays get busy because I'm trying to put your stuff together for the next week, you and the other classes. But I'd love to have your grades out there by Sunday night, and that way Monday I can go in and make your video. All right. Take care.
All right.
Yep.
Thanks.